Let's start very simple and look at a very few factorizations that are extremely useful and may be considered as the basic steps in all simplifications in algebra. So, we all know that most often when we deal with algebra, we are looking to simplify, and that almost always means factorization. Before we look at some interesting ones, let's look at what one would consider the most often used factorizations. So let's not skip them, and straight away let's jump to the two most famous factorizations and analyze them for some time. The first one and the second one, we'll look at both of them. The first one is always possible to factorize. That means for all n, which is an element of natural numbers, an expression of this form, x raised to n minus y raised to n, can always be factorized. And this is equal to, as we all know, x minus y. And the other factor is actually quite easy to remember because it is so symmetric. These are of the powers n minus 1 and then x raised to n minus 2 y plus x raised to n minus 3 y square and so on. And the last term is y raised to n minus 1. How does one convince oneself that this is indeed the factorization? Well, here's a simple logic. If you consider this as an expression of function of x and y, then substitute x is equal to y in f of xy, and we immediately see that f of xy, if x equal to y, is y raised to n minus y raised to n equal to 0. And then by the famous remainder theorem, this would imply that x minus y is a factor. So there is little doubt about where the first factor is coming from. What about the second factor? Now that factor is simply, we can get it by division. So you can see that division of polynomials, which is our favorite lessons in early classes, is extremely useful. So all you need to do is divide x raised to n minus y raised to n minus divided by x minus y, and you will get the second factor. So this factorization is definitely not a surprise. Now what we will do is, there are some gifts of this simple factorization and it's worthwhile mentioning them upfront. So for instance, if we take in the above expression x equal to 1, so just let me write it very clearly. Suppose I take x equal to 1 in the above expression, then I get 1 minus y raised to n is equal to 1 minus y into 1 plus y square, so on, plus y raised to n minus 1. Now here you see that this is a geometric progression sum. And here we have a proof of the famous formula that the geometric progression sum, that is 1 plus y square all the way up to y raised to n minus 1, which has got n terms, is nothing but, please look here, is nothing but 1 minus y raised to n divided by 1 minus y, which is a very famous formula for the geometric progression. So this factorization immediately gives us a formula for the geometric progression. So as you can see, these elementary factorizations have quite a lot of useful inputs. Now, having discussed this, let us go to the second example that is mentioned here, which is, instead of minus, you now have a plus, but this time you have a restriction, and I shall just erase the board quickly and get the example back again. So we now look at the second example that has been written here, which is, I'm going to just write it explicitly here. This is an important one. X raised to 2n plus 1 plus y raised to 2n plus 1 can be factorized as long as the exponent is odd, and that is why they have written it as 2n plus 1, because 2n plus 1 is odd for all n belonging to natural numbers. Now the answer for this is that this is equal to x plus y is a definite factor of this. The other factor is also not very difficult to memorize, and I'm going to presently write it like this: plus x raised to 2n minus 1 y plus x raised to 2n minus 2 y square. And I think I've already made a mistake. This is important, so I'm going to correct my mistake. This is actually minus. So there is an alternating sign now, and you've got to remember this. And then again minus x raised to 2n minus 2 y cube. So please note that whenever the coefficient of y is positive, whenever the coefficient of y is positive, I'm sorry, even, then the sign is positive. Now the last term you can easily guess is y raised to 2n, and now since it is even, you know that it ends with a plus. So with this we have written down the factorization of this expression. So just to give an example, x cube, because the exponent is odd, plus y cube is equal to x plus y, which is the factor here, into x square minus xy plus y square. So this way you can easily write down the factors of x raised to 5 plus y raised to 5, or x raised to 21 plus y raised to 21 as above. So one final word on this is, how do we know, much similar to the argument that was already presented, how do we know that x plus y is a factor? Same idea. Consider this as a function of xy, and then substitute this time x equal to minus y, and then you will see that f of xy equals to 0. And if the exponent is odd, and it's already given that the exponent is odd, and this would imply by the remainder theorem that x plus y is a factor. So what about the other factor? Same reasoning as above. You must get the other factor by division, which is definitely our favorite basic tool. So with that, we've gone through the details of the most commonly used factorizations, and we'll return to this in the next lesson. So let's look at a few more examples, and each of these examples will give us some insights into some of the standard moves in factorization. So here's the first example, and upfront you see that the expression is very symmetric, and in fact that'll be the way in which we are going to narrow down on the answer. So this answer is a very symmetric answer. The factorization gives rise to a wonderfully symmetric expression. And how do we get to this answer? So one way is to look at the symmetry of the problem, and notice that if we can get one factor, we can probably get two more due to symmetry. And the one factor that we will guess is that x is equal to minus y substituted into this expression for the function will actually result in the function being equal to 0, and we will verify that by directly substituting x equal to minus y into the expression. You'll immediately get z cube minus y cube minus y cube minus z cube, and you see that things get neatly cancelled off and we get 0. And this implies that x plus y is a factor of x, y, z. And by symmetry, you can easily guess two more factors. And now that you have three factors and also the degree of the polynomial, the degree is 3, the degree of this polynomial is being 3, one need not look for more factors. So at this stage, what we know is the expression is likely to be some constant times. So I'm just going to write this here. You can expect that f of x, y, z will be some constant times the three factors that we are pretty sure are the factors of the polynomial. And now another standard trick to narrow down on a, we simply plug in some values of a. Let's try x equal to 1 and y is equal to 1 and z equal to 0 on both the LHS and the RHS. The idea is to make sure that both the sides do not go to 0. So therefore, substituting these values here, what you get is 2 cube minus 1 cube minus 1 cube is equal to a times 2 times 1 times 1, and this would mean 6 is equal to 2a, and this would mean that a is equal to 3. So with that, we get the answer as 3 times whatever the factors we have written. So this ends this problem. The key tool is symmetry. And now let's proceed to the next problem. Now, for the next problem, we should do it in at least 3 ways. And one of the answers for this problem is directly related to the problem we've just solved. So let's see how. So this is the question, and this is the polynomial, and it has got a neat answer. Let me write down the answer up front. This will turn out to be minus 3 times x minus y into y minus z into z minus x. So now let's see, like I promised, we'll try to get at this answer at least in 3 different ways. And one of the ways is use our previous problem. So just to quickly remind you what we did just a few minutes ago, x cube plus y cube plus z cube minus, sorry, I'm sorry. So let me just write this again. What we just did was x plus y plus z whole cube minus x cube minus y cube minus z cube is equal to 3 times x plus y, y plus z, z plus x. So what we shall do here is instead of x minus y, we'll replace it by another variable capital X, and instead of this, we'll replace it by another variable capital Y, and instead of this, we shall replace it by another variable capital Z. So we're looking for the factors of x cube plus y cube plus z cube. Now we take the cube from here and see that x cube plus y cube plus z cube is actually equal to x plus y plus z whole cube minus 3 into x plus y into y plus z into z plus x. This is equal to x cube plus y cube plus z cube. Now notice, and this is the key observation here, notice that x plus y plus z is equal to 0. Just to make sure that everybody is with me, if you add x minus y to y minus z to z minus x, you get 0. Now what that would mean, if you put x plus y plus z equal to 0, is that x cube plus y cube plus z cube is equal to minus 3 into these factors, and that would mean that x cube plus y cube plus z cube here is actually equal to 3 into x plus y into y plus z into minus 3, sorry, minus is important, minus 3 into z plus x. And now what is x plus y? X plus y is, I'm just going to write it here, x plus y is nothing but x minus y plus y minus z, which is nothing but x minus z. So let me directly write down the final answer now. So which means that this is equal to minus 3, mind you, into x minus z into what is y plus z. Y plus z is y minus x, and that leaves you with the last factor, z plus x is z minus y. So this is the end of the problem, but I promised 2 more methods to deal with this problem. So let's get to the discussion of the other 2. So the second one that I think I would like to emphasize is something that always plays a role. If you can guess one factor here, so in this case it's quite easy to verify that x minus y is one of the factors. And how? So let's say that I put x equal to y into the above expression, then the first factor becomes 0 plus x minus y, so y minus z whole cube plus z minus y whole cube, and you can see that these two will cancel each other, and that will give us 0. So this implies by the factor theorem then that x minus y is a factor, and similarly now you can get the other two factors as y minus z and z minus x. And finally we notice that this is of degree 3, and we already got 3 factors. So like one of the previous problems, we write that f of x, y, z is equal to some constant times x minus y and y minus z and z minus x, and we plug in values to determine the values of a. It turns out to be minus 3. So this was indeed very similar to one of the problems discussed earlier, but now the last method that I'm going to discuss about this problem is definitely, if you're looking at it for the first time, you must look it up, and it's a very important concept in basic algebra. So let me talk about it. So what you have to notice here in this case is that the so-called function is, now this is a big word, so if you're hearing it for the first time, you must go and learn this up. It's a very simple idea, and you must look it up, and it has some significance, as I will come to in a minute. If you notice that the function is antisymmetric, now why am I calling this function antisymmetric? So if you notice that f of x, y, z is equal to minus, now I'm interchanging the two variables, f of y, x, z, but with the minus sign, then we can say that the function is antisymmetric. Now there is a very wonderful theorem about the representation of antisymmetric functions. So any antisymmetric function will have f, such a function f of x, y, z will definitely have x minus y, y minus z, x minus z as into something, into some f star x, y, z as factors. So this is an important representation theorem for antisymmetric functions. Now, if you can notice that this is antisymmetric, then upfront you can be able to, as you can see here, we can easily verify that if this is represented as f of x, y, z, and now you now notice that f of y, x, z is actually equal to y minus x whole cube plus x minus z whole cube plus z minus y whole cube, and compare it with the previous function. So you can see here that these two terms are negative of each other, and these two terms are negative of each other, and these two terms are negative of each other, which means that definitely this is equal to minus of x, y, z, and this implies that the function is antisymmetric. So this is how you exploit that the function is antisymmetric, and we will definitely come across more examples in our lessons where spotting that the function is antisymmetric will immediately give us three factors, namely, I repeat, x minus y, y minus z, and z minus x as three of the factors for the antisymmetric function. So we shall definitely come across more such examples, and we'll stop this lesson now. Thank you.